Bismillahirrahmanirrahim. Assalamualaikum and a very good day. We move on to Chapter 2, Determination of Rate Law. If you can recall what is a rate law or rate law equation, so it's given by negative RA is equal to KCA power of, I just put it alpha. So rate law equation is an equation that relates rate of reaction and rate constant, which consists of temperature and then concentration of the reactant. Alpha here is the reaction order, whether if alpha is equal to 1, so the reaction order is 1. Alpha equal to 2, reaction order is equal to 2. So determination of rate law meaning that you are going to determine what is the value of K and what is the order of the reaction, alpha. Before we move on to the content of this chapter, so let's have a quick introduction with types of reactor. So this is batch reactor. You can have many designs, but we can simply sketch the diagram as this one. A tank, most of the time is closed system, meaning that there is no mass flow rate in and mass flow rate out. So you may start with NA naught, the initial, this is a number of mole at the initial, and then after certain reaction time, then you are going to measure what is the concentration or number of mole for species A. Okay, I always put concentration because most of the time for batch, you'll have constant volume for which number of mole divided by volume will become concentration. So basically we are only interested to know what is the concentration of species A, that is the key reactant. Okay, the initial and after the reaction time. So batch reactor mainly used for small scale operation, suitable for slow reactions, mainly used for liquid phase reaction. Charge in cleanup times can be large, so it may take some time to set up and cleaning up the reactor. Okay, this is the basic or something that is common related to reactor types. Batch reactor. It doesn't mean that batch reactor must have all these criteria. No, this is just a common description of a batch reactor. Next is continuous stirred tank reactor. So the word continuous tank reactor. Okay, as explained by the name of the reactor. So continuous meaning you have a continuous mass flow rate in and mass flow rate out. So it's no longer number of mole. We always refer to the concentration. So Ca naught and Ca. If you have two reactants, for example A plus B, C plus D, so you may have Cb naught and then will be Cb. If you have some product, obviously you'll have C here, then you have Cd as well. Okay, but most of the time we are only interested to know what is the concentration of species A, which is the key reactant, at the initial and the final. Because later we may deduce an equation that relates CB naught and CA naught, an equation that relates CB and CA naught, even CA with CA naught. Okay, so CA naught is very important, and other important parameters is the conversion X. So again, we have an impeller or a stirrer in a CSTR. So the description, steady state operation used in series. So steady state. What is steady state? You learn in fluid mechanics. So steady states meaning the conditions do not change with time. The condition here is referring to the concentration, the most important parameter, temperature or pressure. So at any time from morning to night, it keeps given the same value. If the concentration that's concentration in the reactor is, for example, 5 mole per liter, yes, it will be 5 mole per liter from morning to night. Let's say this is concentration at the final. Okay, because it is steady state operation. So it is different to batch reactor. Batch reactor is unsteady state, meaning condition change with time. Number of mole at the initial, number of mole at the final. In between times, let's say 1 hour, they'll keep changing from Na0 to Na. Okay, let's come back to this CSTR. Commonly used in series. So you have more than one CSTR, then you arrange it in series. We will learn what is the advantage to have series CSTR in the next chapter. Next, good mixing leads to uniform concentration and temperature, mainly used for liquid phase reaction, suitable for viscous liquids. The last ideal reactor is called PFR, plug flow reactor. So plug flow reactor, most commonly it is a tube. Okay, it is a tube. So you'll have mass flow in, mass flow out. And again, it is a steady state operation. When it is continuous system, meaning that it is steady state operation. So this is also a continuous system. So you have similar case, you have CA0 and then you have CA. So for PFR is suitable for fast reaction, most commonly used for gas phase reaction. However, temperature control is quite difficult and there are no moving parts, meaning there is no impeller or stirrer. So this is arrangement of plug flow reactor, an example. So you can see there are a lot of tubes here. Okay, there are many tubes. So the reactant will pass the tubes. Okay. There is one more reactor which is mentioned in your course outcome, that is PBR, packed bag reactor. So for packed bag reactor, it's similar to PFR. The fundamental is PFR, except you have a bed of catalyst. Reaction only can happen when it's past this catalyst. Okay, when you have a bed of catalyst, it's called packed bed reactor. Okay, and then the main difference is when it's PFR, we are dealing with volume of the working fluid as reactant, or volume of the reactant, whereby for packed bed reactor, all the equations are similar except all V is replaced by capital W, that is weight of catalyst. Alright, let's look at the course learning outcome for chapter 2, determination of rate law. At the end of this chapter, students should be able to interpret batch reactor data because this is the simplest reactor. Number 2, examine rate law using differential method of analysis. So under differential, there are two types. One is graphical, another one is numerical. 3, analyze integral methods of analysis. And last one, evaluate the rate law based on the method of initial rates and half-life. So basically, there are 4 methods how to determine the rate law. Number 1 is differential method. We call it differential because it has the differential form of equation. Under differential, you may have graphical and you may have numerical. Method number 2 is integral. Integral. We call it integral because you are going to integrate the equation. Number 3 is method of initial rates. So method of initial rates. Initial rates. And last one is half-life given by the half. Right? For the lecture outline, there are 2 big subtopics. Number 1 is interpretation of batch reactor data. And number 2 is method of analysis, meaning all the 4 methods. Move on to the first subtopic, interpretation of batch reactor data. Okay, let's recap several parameters which is very important. Okay, the first one is conversion, X. Number of mole of chemical species I that have reacted per mole of I fed to the system. Okay, I already explained this one and I'll explain it again. You have a batch reactor. You may write this one, but it's not meaning it is continuous. It's a batch system, meaning that you have your CE0, then you have your CA. Okay, for constant volume. But we stick to, when it's batch, we always stick for NA0 and NA instead of concentration. Okay, so let's say this is 10 mole. You measure the species, the concentration of species A, the reactant. You should know what is the number of mole or concentration of the reactants that you are going to put it in the reactor. So here, the number of mole, initial number of mole is 10 mole. And then after certain reaction time, you take the sample and then do analysis using all the instrumentation available in the market. Then you determine value of number of mole. So the remaining number of mole here, let's say Na is 1 mole. Alright. So conversion, so species A obviously been converted from in the reaction. So it is reduced from 10 to 1. So conversion will be Na0 minus Na divided by Na0. So 10 minus 1 divided by 10. So it is 0.9. Okay, that is conversion. So what you can say here, conversion is number of mole of species I that have reacted per mole of I fed to the system. So number of mole of I reacted, obviously it is 10 minus 1, which is equal to 9. Agree? There was 9 moles of species A being reacted. So divide by number of mole of I fed, that is 10. So 0.9. Right, this one already explained it. So this is the equation, and you may further simplify, and A naught divide by an A naught, it will become 1. Okay, then you may have in terms of concentration when you divide it by the volume. Alright, so this is the differential form of equation. How to get this one? Take this XA and the last equation, do the differentiation. Okay, X is equal to 1 minus CA divided by CA naught. So dXA integrate to respect to CA. Then you get this equation. So in this slide, I'll show it. XA is equal to 1 minus CA over CA naught. Differentiate dXA. Differentiate with respect of CA. Okay, so what left is negative 1 over CA naught, because CA naught is a constant. Then you may rearrange this equation, you get this equation. Alright, only applicable to constant volume batch reactor. Remember, constant volume. Although they have a batch reactor which is not have constant volume. We will learn it in the next chapter. For a non-constant volume system, relationship between X and C is necessary. X, conversion and concentration is necessary. Alright, so in this example, we have the rate law, the one that I mentioned earlier. Determination of rate law, you are going to determine what is the value of rate constant and what is the reaction or the alpha. Okay, what we are going to do is, first, still remember this equation is come from the definition of rate of reaction itself. So it is change in concentration with respect to time, and is given by Ka Ca power alpha. So basically, we are going to utilize these two main equations, the rate law equation and the mole balance. Okay, combining mole balance and rate law. So basically, this comes from the mole balance. So this combination is in terms of measurable variables, that is time and concentration. Constant volume batch reactor is referred to volume of reaction mixture which is not the volume of the reactor. Right? That is what I always mention. Your reactor might be slightly bigger than the volume of the reaction mixture. But we always take our V in Fogler as the volume of reactor. From material balance, we already have this equation for several times. I hope it's already in your mind. Okay, this is rate of reaction for liquid phase. For gas phase, we are going to have it in terms of pressure. Change of pressure. In this case, it is a partial pressure with respect to time. Okay, so basically it's come from the ideal gas law, for which volume you may represent it by RT over P. Because PV is equal to nRT, then V is equal to nRT over P. So you may replace this V by RT over P. The rate of reaction of a component can be given by the rate of change of concentration or partial pressure. Okay. It depends on the phase of the reactant. Okay, this is the algorithm. So if you read Faulkner, they always mention according to the algorithm listed or illustrated by figure 1, for example. So this algorithm is actually the steps. Okay, how to analyze rate data for batch reactor. Number 1, postulate rate law, meaning that you need to have an initial gas. Okay, what is the rate law? So the most common one is we will put it as negative RA is equal to KCA power alpha. Number 2, identify reactor type and mole balance. Because mole balance is according to the reactor type. The simplest reactor is batch reactor. So in our subtopic here, we are referring to batch reactor. Although you may also determine rate law using CSTR. Okay, the third step is data in terms of measurable variable. So we need to rearrange the formula so that you have it in terms of measurable variable. Simplify and then analyze data using one of the method, whether it's differential, integral, initial rate, or half-life. So differential, you may have graphical, you may have numerical. Okay, the second part of chapter 2 is methods of analysis. There are 4, as I mentioned earlier: differential, integral, initial rates, and half-life. Under differential, you may have graphical and you may have numerical. I repeat it again. What is the main purpose of determination of rate law? Is to determine the reaction order and reaction rate constant K. Okay, we start with first method, differential method. For irreversible reaction, the reaction order and specific rate constant can be determined by numerically differentiating concentration versus time data. It is applicable when the rate is essentially a function of the concentration of only one reactant. Okay, remember, it's only applicable if you have only one reactant. If there are more than one, yes, it can be used also, but we have additional step. Consider a reaction carried out isothermally in the constant volume batch reactor, and the concentration is a function of time. So basically the raw data will be time and concentration. Time, concentration. Because it's batch, right? So let's say you have 0, 1, 2, 3, 4, 5 minutes, and then you need to measure what is the concentration at respective time. Then you may analyze it using a differential method. Okay, the steps. By combining mole balance and power law model, so this is what we call power law model. Negative RA equal to KCA power to alpha. Okay, mole balance is this one. Negative RA is equal to negative dCA over dt. Sometimes we just drop the negative sign. So what we need to do next is taking the natural log for both sides. Okay, I hope you know how to introduce the natural log at both sides for this equation. Okay, then you'll have this equation. Okay, having this one, you may have it in this form, for which alpha will be the slope, ln k will be the intercept. So meaning that you may solve the equation and the rate constant and also the power of reaction. Okay, now how to get this negative dCA over dt? So this method is actually to determine what is the value of negative dCA over dt, because previously what you did in your experiment is to get the value of concentration at respective time. That is not dCA over dt. So you need to further analyze this data. Okay, so there are two methods, graphical or numerical. Once you determine your negative dCA over dt, then you may plot the graph to obtain alpha and k. Alright. In this slide, the plot is illustrate the y-axis, which is ln negative dCA over dt versus ln Ca, for which the slope is equal to alpha and the intercept is equal to rate constant k. So remember, this equation is actually come from this. Okay, so negative RA is equal to also negative dCA over dt. The two important equations that you are going to combine. So what you have is negative dCA over dt is equal to KCA alpha. So K obviously equal to negative dCA over dt divided by Ca alpha. Okay, which is equivalent to this equation. So how to get negative dCA? As I mentioned earlier, by graphical differentiation, numerical differentiation, or differentiation of a polynomial fit to the data. We only focus 1 and 2 methods if it is in the final examination, whereby you need to sit for final physically in the examination hall. For method number 3, you need to have software. Okay, meaning if this physically you need to attend or sit for final exam, the third method will not be asked. But as a chemical engineering student or engineering student, you should know how to use software to do the differentiation, because it's simple. It just needs you to be exposed to this kind of methods. Okay, in this example, I will use polymath to do the differentiation of a polynomial fit to the data. We start with a graphical method. Okay, graphical method meaning you need to prepare a graph paper. Okay, this is actually the summary. Tabulate CAI and TI, meaning the concentration at respective time for each interval. Calculate delta C and delta T. So if you look at here, delta T is T1 minus T0. They put it in the center, in the middle, because this data is referring to this first row and second row. Okay, then delta CA is C1 minus C0. Then you'll have delta CA divided by delta T. Change in concentration divided by change in reaction time. Alright, so those you are going to repeat it. The second row for delta T is combination of data between T1 and T2. Okay, I hope it's clear. Okay, if you look at the last column, that is the negative dCA over dt that we are going to use it to plot the graph. Okay, so dCA over dt is come from the information that we get from the first row and second row. But this is by graphical method. We'll see how. If you look at this statement, this method accentuates measurement error. Okay, what does it mean? Because it is graphical methods, meaning you may have produced some noticeable error, right? So by graphical methods, what we are going to do is, before the last column, you have this one, delta CA divided by delta T, and you are going to plot an histogram, okay? A histogram having negative delta CA over delta T as y-axis and the time as your x-axis. So if you look at this one, once you plot the diagram or the histogram, you need to identify the area. Okay, so if you look at these steps, delta x, delta y, plot this, then try to find area A, which is equal to area B. Okay, so this is area A, this is area B. It is, you need to identify the point here, which is very close in terms of the area. What I would suggest to you is, first, find the middle point. See this one? Middle point here. And middle point here. Okay. Then try to have almost similar area by connecting the middle point for each of the histogram. Okay. If I can make it bigger, this is your histogram. Okay, find the middle point first. This is middle, this is middle. Then try to plot so that this area is equal to this area. Okay, by passing the middle point. And then this area must be similar to B, must be similar to okay. This C must be similar to D. Alright.